MCV4U, Chapter 5, Lesson 7-ish on trig derivatives. And the warm-up here is a lot of the lessons sort of. Now, this was from the investigations earlier, and if we had f at x is sine x, well, what's the derivative then? The derivative of sine is cos. And we saw that in a bunch of different ways when we did the investigations. And what's the derivative of cos? Was negative sine x. And these are kind of derivative facts that you got to remember, just like the product rule and the quotient rule and the chain rule and all those things. You got to remember them. And so if they get more complicated, our derivative rules still apply. So here, differentiate. I take the derivative with respect to x. Well, the derivative of sine is cos. But this is also a chain rule. So I got to take the derivative of the inside thing, and that becomes 4, because the derivative of 4x is just 4, and tidy that up a little bit. Here, the derivative of cos of x squared, well, I take the derivative of cos, and it's negative sine of whatever. And then the derivative of the whatever is 2x, so I tidy that up, and I get that. Notice that that's different. These two are different, right? This is just the x is squared on the inside. And on this one, this means this. Right? This means this sort of thing. But it was, we put the 2 there because we were lazy, didn't want to write brackets, I guess. So the derivative of that is 2 cos x. That's the derivative of the mother function. And the derivative of the inside thing, derivative of cos, is negative sine x, and then I tidy that up, and this actually is one of our trig identities. Hopefully that was ringing a bell. 2 cos x sine x is actually sine 2x. Now, would you have to do that? No, not necessarily, but if you're going to take the derivative of this to get to test for concavity or something like that, this is an easier derivative than this, because taking the derivative of this would be a product rule. The derivative of this would be a tiny chain rule, and so it might make sense to change that form, even though I'd mark this completely right if you stop there. All right. So one of the things we're asked to do is just take the derivative of functions using our trig rules, and just like we have for any other function. So part of the lesson, geez, was right there. Can we take the derivative when we have sines and coses involved instead of exponential functions or polynomial functions or rational functions, that sort of thing? Where does this come from are these facts, right? And these facts are based from, we have to prove them, right? We investigated them, a few classes ago. We got the facts right, but we want to prove them. And some people were asked to do this from first principles, and that's what we're talking about. So y prime is the limit as h approaches 0 of I'm going to use the f notation, because that way I can write down I can use this sort of thing, right? This is the definition of first principles. This is what we have to have memorized. But f at x is just sine x, right? That's what we want to take the derivative of. So f at x plus h is sine of x plus h. Well, the sine of x plus h, remember there's a trig identity that's involved here. The sine of a plus b is, well, how do I remember these? Well, I remember cos is cos minus sine. And so this is the other one that has the pattern. Sine a, cos b, plus, sine's the one that doesn't change signs, the cos of a, the sine of b. And so the function that we're interested in, sine of x plus h, the x is the a and the h is the b. Sine of x cos of h plus the cos of x, the sine of h. And that part there goes in for here, and so let's write that. All of this is going to end up being cos. We know that because we investigated it earlier, right? So I have this thing is this thing. All over h. Now, how am I going to deal with this? Well, again, the sine x and the cos x, well, they don't have anything to do with the limit index, right? So we kind of want to separate them if we can, and that's what we're going to do. So the ones with the sine x's, I'm going to put those together. Plus cos x sine, and I've split it up. Do you see how I've split it up? Because what I'm going to do now is I'm going to split these limits up and pull the cos x and sine x. You see how the sine x, there's a common factor here. So I got cos h minus 1 all over h plus cos x sine h over h. And yeah, I'm working away. Again, the sine x has got nothing to do with the h, so I can pull it out front. Same thing here, right? I'm going to split this limit up. The limit of a sum is the sum of the limits, and I'm going to pull the cos x out front. And we're kind of stuck now because I don't know how to evaluate these limits. And certainly I could do the pound it into a calculator, but that's not really much fun. These are just like when we did the logarithm, natural exponential function. These are limits that we kind of have to know somehow. And if we look at what we know what the answer is, there's no sine x in the derivative. This has to be 0. This has to be 1. And because we know the answer is cos x, right? So we know this answer is cos x, and it's all fine and dandy. But how do I know that this is true? And this is an important discussion. Oops, this one is 0. And the limit as h approaches 0 of sine h over h is equal to 1. Now, why is this true? Well, again, I could use my calculator. I could do that, but I'm actually going to go through a very important discussion about why this is true on a separate video. If you don't have time to digest it, then that's fine. It's not part of the course, but it's part of every single first-year university calculus course is this discussion, and it will help you greatly if you have seen it before then, and it'll help you understand why these two things are true. What I'm expecting you to know is you have to know that this is the case. You kind of have to memorize these facts, and the explanation of why will come on a separate video, something called the squeeze theorem, and I'll do that later. But for now, we've just proven that that's true, and we can use, there's the squeeze theorem handout, and we'll go through that in a different video, separate video. So can I prove then that this is true? Well, I can from first principles again, but we just did it, right? And I'm actually going to use a little fact. So I want to show that the derivative of cos x is equal to this. Well, I'm going to use something we know of trig graphs. I'm going to use an identity. So this is y equals cos x. But y equals cos x, this is pi here, is just sine moved over, isn't it? Right? So if I do this sort of thing, I've just moved, I've taken cos and I've moved sine left pi over 2, right? And then I get cos. So if I wanted to do the derivative of cos, I could do the derivative of sine moved over left pi over 2, couldn't I? If I wanted to. Right, absolutely I could. So I know the derivative of sine. The derivative of sine is just cos. Well, what's cos of x plus pi over 2? Well, that's negative sine x, right? If I moved, one way to think of it is if I move this blue one, which is cos, left pi over 2, I'm going to get negative sine, right? And so I can kind of be a little bit tricksy with my trig derivatives by using some of the identities that I knew before. Certainly, another way to think of this would have been, well, if I wanted to take the derivative of this, sine of x plus pi over 2, could I just use that same formula that I had before and take the derivative of it? Cos of pi over 2 is 0, so this is 0. And then this is, what's sine of pi over 2? Sine of pi over 2 is 1. And then take the derivative of it. Could I do that? Yes, absolutely I could have. And that might be a way that I could do it as well. But for us, really, just remembering this fact is good enough. Now we know we've got those two things proven. Remember, this other video on the squeeze theorem is an important video that you should watch as well. But back to regular, boring old, now that we know the new rules, let's do a million different calculus things, like finding critical points or finding equations of tangents or sketching curves or whatever. Find the critical points of that graph. Well, critical points occur, remember, where y prime equals 0 or y prime dne. Notice that this is a exponential function, even though we've got a crazy thing in the top here, but it's going to be defined for all values. So we're going to see the derivative exists for all values. I'm going to take the derivative. So the derivative of e to the exponent whatever is e to the exponent whatever, right? Remember, the derivative of e to the x is just e to the x. Now the x happens to be a complicated function, so I do have to take the derivative of the inside thing. The derivative of the inside thing, the derivative of sine is cos. The derivative of cos is negative sine. And so I get the critical points when this nasty big thing is equal to 0. So set dy by dx equals to 0. And I see that there's two factors. Oops. This one gives me no solutions, right? Because e to the exponent anything is never 0. So there's no solutions here. But here I'm going to have cos x minus sine x equals 0. And then that is going to have some solutions. In fact, I have to remember how to solve some trig equations. One way is I suppose I could try and remember where cos x and sine x are equal, but I'm going to divide by cos x, and then I get tan x. So when is tan x equal to 1? Well, tan x is equal to 1. It's positive, right? So cast rule, tan is positive in this quadrant and this quadrant. The raw related acute angle is pi over 4. So my x1 is pi over 4 plus 2 pi n, right? There's an infinite number of solutions. And here's my second solution there. x2 is pi plus pi over 4 plus 2 pi n. and I get an infinite number of solutions, infinite number of critical points, which is pretty interesting. Collect like terms there. So therefore, there are critical points at pi over 4, 5 pi over 4, and then every pi over 4 after that, right? Because 2 pi over 4 is 8 pi over 4, right? So 8 pi over 4, that's 9 pi over 4. Every 4 pi over 4, I'm going to get a new critical point. Dot, dot, dot. An infinite number of critical points. Dandy. Okay, so I'm going to pick up example 4 in part 2. Remember, you also have the business about the squeeze theorem to watch. So part 2, example 4 coming up.